This is with Hemal, the world-renowned, and we're back to talk about going from concept to PCB, this time in the design of a vision system, which this is a really cool thing. And one of the differentiators we have here at DevHeads is that, you know, a bunch of the guys are working on things that are either similar, in some cases the same. If you've been with us recently, you'll notice that Ming has had a session on developing a vision system that can identify abandoned objects. And here, Hemel's picking up on that from the hardware side, where Ming is looking at it from Yocto and OpenCV and above at the application layer. Hemel is now looking at it at the hardware side and saying, okay, if we really wanted to build our own system, what are some of the considerations we'd have to take into account for in order to support what Ming's doing. So now we're starting to see a lot of the synergies come into play, and we're really excited about this. Obviously excited to have Hemal on board. He is a treat to work with and awesome resource for you guys if you need one in the PCB and hardware design space. We do have a couple of housekeeping items to get through. I'll try to go through these as quickly as possible. I know this is like brushing your teeth. But today's session is probably going to consist of like 30 to 40 minutes worth of presentation from Hemal, and then we'll have 10 or 15, maybe 20 minutes worth of Q&A at the end of the hour where you can ask him questions. Make sure that if you are not able to if you're not able to get your questions asked or responded to, that you join us in our Discord server or online. The online web address is devheads.io. And the Discord server is discord.gg/devheads. Hemal, Amesh, Ming, Zach, and tons of other experienced pro IoT and embedded developers are there who can answer your questions on anything from protocol stacks to PCB design. In terms of the platform itself, if you just saw my message on the location of the Discord channel, that means you're in the Livestorm meetup platform. And there, you're going to have a couple of options in case something goes wrong. So if you can't hear or see or type or anything like that, the first thing to do is to go to the help button, which is in the lower left of the interface. That has a wizard that will walk you through various steps and hopefully get you back involved in the event in no time. If you are not there, or if you're still having problems, I'd recommend, if you're watching through a platform like Discord, for example, quit the app and view it through the browser. That's been a problem. Another thing is you might want to check your bandwidth. Go to speedtest.net. If you're pulling less than 5 megabits per second down, you may have issues with the stream. You can always try quitting whatever application you're in and then coming back in. Like back in the video game days, just blow on it and that might fix it. And then the other thing is, if you have problems, just drop a note into whatever your respective chat is and put @Brandon Lewis or @TechieLou. That's me, and I'll get around to it and see if I can help you get back up online. All right. There are a couple of other notes about places where we've got resources and things that might be helpful to you. I'll drop those into the chat and Livestorm and the other session or the other platforms, as I mentioned, but I don't want to take up too much more time. At this point, I'm going to hand it off to you, Hemal. Why don't you take it away on concept to PCB?
Thank you so much, Brendan, for the intro and housekeeping stuff. And it's great to be back again this week. Last week we had a talk about fundamentals on PCB, which also had a lot of information and a lot of small bits and pieces of information that might be useful. So maybe after this talk, if you haven't already checked it out, you can go to the YouTube channel and have a look at it as well. So today is going to be sort of like a continuation of that talk. And today we're going to talk about how do we take our concept or a product brief and how we go to a PCB, and we'll talk about how different ways to do it. Before we jump into it, I'm a hardware designer, and I have designed boards from ranging from microcontrollers to small IoT devices, and all the way to big carrier boards, which has high-speed interfaces and things like that. So why are we here? So first of all, at the end of this talk, I promise you will have a clear understanding on how to take a product brief and take it into and take it in a systematic way to a product. And we'll also see how we can break down the uh, product requirements and convert those into our PCB requirements that are more technical. And along the way, we'll also take a look at various product briefs, uh, big and small. So when we start to design a new um, hardware or a piece of product, there are usually, what I've found, there are two ways to do it. One is mostly a wrong way to do it, and one is a mostly a right way to do it. So first we'll talk about the mostly the wrong way to do it. And what I mean by this is, when you are asking a question, when you receive a product requirement and you ask yourself a question, can I make it run on some platform? That is, in my view, is not the right way to do it. But I have been there, and I have also done this mistake. And I asked the question whether if it can run on a certain platform. So, for example, if you're a beginner and you have started to learn, let's say, the Arduino platform, and you have a lot of small examples running. You have some motor controls done. You have done some stepper motor. You have some buttons and LEDs, and now you get a requirement of a small project that incorporates all of these. And you ask yourself that, can I run this on the Arduino platform? And because you have all the bits and pieces, you just need to combine those. And yeah, the answer is yes, you can do it, and you deliver it. Um, Nothing inherently wrong with that. It works. You deliver the product. It's fine. It's working. But in the long run, it's not the right approach. So and this also goes for not only for the hardware, but for software as well. So when you're writing firmware, there are certain methods or certain ways you can write the firmware. So there is like one is a super loop programming way. There is another one is using interrupt based programming, and the third might be an RTOS and something else which I don't know about. And if you're trying to incorporate the same type of programming into all of the projects that you're getting, you're not probably doing yourself a favor, because you're doing the same thing again and again, and no doubt it works, and you're happy, the customer is happy, but in the long run, you are limiting yourself by doing this. um, there's also one more quirk from the hardware side is you sometimes become a fanboy. So for me personally, I was a AVR fanboy. So this was before the Atmel was sold to Microchip. I was a and I started working with AVRs, and I just kept working with those, and ultimately for any project that came through, I would always look at the AVR set of chips. And once you're in, when you are familiar with something and you are starting with that, you keep on using this, and unknowingly you start to you come into a camp, and then you start defending it, and not really looking at the other stuff. So for example, it could be PIC, or it could be the STM. But it's a natural way of growing, and you need to take a step back and look at all the things that are available, and not to become a fanboy. So these are some of the ways that are you should not do it this way. So when you get a project requirements, don't try to fit your requirements into the project. Try to fit the project requirements into your PCB or your hardware requirements. So what is mostly the right way to do it? First of all is to understand the requirements, what the product actually needs. What is the what we call this way is also called as a top-down approach. What we talked about before, you could also say it is like a bottom-up approach, but for me, what worked for me in the long run and what did justice to the product was the top-down approach, where you get a clear overview of your requirements, and then you zoom in and you start breaking down the requirements into smaller and smaller chunks. And we will go through this sort of an exercise with one of the example product briefs. And I'll also keep on updating or keep on telling you some stories or anecdotes that I remember. And this way, you'll be able to do justice to the product, and it will also uh, be a quality product. And there's always this three it's called a triangle. When each corner there's cost, time, and quality, and they say you can only have two of them. So if you want to have a cost-effective product, it's gonna take more time or have a less quality, or yeah. So that's the right way to do it. So we'll go a bit more deeper, and we'll start from the most zoomed out way, and we'll see we get the product brief. So when we get the product brief, first of all, we need to understand what is the pain point the product is solving. Sometimes the customer don't know uh, if that is the right way to solve the problem, or um, if they think this is the way to solve it, but it might not be the right way to do it. And also, we need to be aware of the XY problem. Um, I'm not sure how many of you know about the XY problem. You can just hit react if you know about the XY problem, but I'll go through it anyway. So the XY problem is simply, it comes from the software domain, but we can apply it almost anywhere. Say you have a problem which is X, and you think Y, doing Y can solve the problem. And then you go out in the world and you're asking people, how can I accomplish, or how can I execute Y? So you really need to understand that this is going to happen, and you need to go to X somehow, and by talking with your customer. Um, I'll share quickly two examples where this happened. This is like real life examples where uh, a, a client came to me. He was from the software background, and he was a software guy, also write firmware. And he came to me, I want a device that has two ESP32s, and it can do certain things. But I was a bit confused, like why you need to have two ESP32s. Um, Turns out he needed more UARTs on the device than that are supported by ESP32. So I think that it has three, but he needed like six or five of them. So he said, well, I'll just use two ESP32s, and that's how I'll solve the problem. So this is the classic example of a XY problem where he needed more UARTs. The problem was having more UARTs, but he thought having two ESP would solve it, and he was asking me to design something which has two ESP32s on it. So that is one a real life example that happened a couple of months ago. And another one was a fairly recent one that happened on nowhere else but in DevHeads here itself, where there was people working on a project where they had the motor, but they didn't have the driver. So they were asking to find the driver for this motor, and it needed to be done very quickly. But then after talking with them, we realized that they actually needed this whole thing for a small demo, and that demo already had a motor and the driver. So we sort of ended up just using that, and we were able to um, take a pause on it, and then we will be able to define the motor, define the driver in the proper way. So this is what you need to be very be aware of when you are getting any requirements from your clients. Is is it what real needs and what problem it is solving? So once you have done all of that, then you start at the high level requirements that are that this will start slowly getting more and more technical. So the product brief was just talking about the problem, how it is solving it on a very, very high level. Then you go a level deeper, where you have higher level requirements, where you talk about all these things that are listed on the slide. You think about all of them, but you don't think about them in sequence. So you don't think about the processing power, then the communication, then the interfaces. You have to think about all of them at once, almost at the same time. So, for example, from the previous example of the communications, um, let's say if you have a small microcontroller, you want to design a microcontroller based product, and it needs to have, let's say, 10 UARTs. Now, this 10 UARTs, if you want to use it, it will probably be in some high-end chip, which is too powerful for your application, but you might end up using that because you need the interfaces. So it's okay to have a higher processing power than you actually need. Then there are interfaces. Again, there are some interfaces, like let's say if you have an PCIe requirement for a device, then you probably need some microprocessor. You might not even be able to do this with a microcontroller, but the amount of computing power that you need might not be that much that requires a microprocessor. But just because of the interface, you have to use a different processor. Let's talk about some stuff at random. Let's say the cost. When I say cost at this level, don't confuse this with the bill of the materials, because when we talk about cost at this level, it is including of the bill of the material, the cost of the PCB, the cost of the assembly, and also the cost of the enclosure. So when we are talking about cost at this level, it is cost of everything combined. Then about the power constraints. So in this one, how is the device powered? Does it have a battery in it? Is it powered by some DC power supply, or do we have to have a SMPS into it integrated? How much power we are putting into it? Let's say we have a very high power device. Let's say it is 100 watt. It consumes 100 watt of power, and let's say even if your design is 90% efficient, it is going to give out 10 watts of power as heat. So you need to manage that heat as well. So then your thermal considerations also come into play. Next, you can talk about the data flow. Data flow, what I mean here is, you have a device. It's when your hardware device, it's basically a component in the grand scheme of things, and it takes in the data from somewhere and then sends it somewhere else. That's the basic function of if you break down any of the hardware. say you have a sensor and an actuator or a motor. So it takes in the data, processes it, and then does something based off of that data, or it can just send the data. So, and if there are some uh, streaming of data going on, you also need to be aware of what kind of protocols are being used. So you need to be aware of a little bit of the software side of things, on how things are gonna go when the product is built. So it shouldn't be like that. Okay, here's the hardware that you require. Now my work is done, and now it's up to the software guys to take care of. You also need to have a little bit of idea of how the things are going to go within on the software side as well, because some of those will also impact on what you are doing on the hardware side. So for example, if there is a uh, if you have some data, let's say there's a vision system that we are going to talk about. It is getting the data, and then we are sending it off using Wi-Fi, and you need to know that and if you don't add a LAN port to it, you might be limiting yourself, or you might not be doing the product the justice that it needs to be a high a reliable product and a high quality product, just because you didn't thought of adding a LAN port. It's just a very trivial example, but there are a bit of nuances that goes with it. So it's always better to have a little bit of idea on how the data flow goes. Next is compliance. This is also one of the big things when you are writing your high-level requirements, is what sort of certifications does this product is going to need. So this will also depend on where the product is going to be deployed. What is the application? So is it automotive? Is it medical? Is it industrial? Is it military? All of those things, they have different compliance. Is it maybe in oil and gas industry? And they have their different set of compliances, that if you are designing a product with that in mind, then when your product is ready, it is ready for that compliance, rather than designing the product and having everything ready, and then you realize that, uh-oh, my product is really not compatible with this certain standards that it is going into. So then you have to go back to the drawing board and make the changes, which again is going to be more time consuming, and it's going to cost the client not only money but also time as well. On other side of the compliance, there's these ISM bands that are there, which use certain frequencies. So certain frequencies are allowed in some countries, but certain frequencies are not allowed. If I'm not wrong, I think this 433 megahertz band is not allowed in the US, but it is allowed in the European region. Correct me if I'm wrong, but don't quote me on that. But there are some differences on which band can be used in which country. So you need to design your hardware in a way for that particular in a region specific way. So then these are the hardware level, the high level requirements that you need to gather. And after you have done this, the next step is to design the architecture of the whole system. So making architecture is nothing but just making a simple a block diagram of things and connecting them together. And you can see in the product in its own entirety. And I try to make the block diagrams in such a way that each of these, or most of them, they could convert into sort of like schematic sheets later down the line. So here is an example block diagram that we have gotten from the client. Now, in this case, we are sort of very lucky, because the client has told us to use a particular hardware for processing. So we don't have to think about any other um, processors and things like that to in this case. So if you find yourself in this case that you need to use this for some reason, and so you just go with it. And it's basically, there is a camera, and if there is a PCB which is not not handled by, it doesn't have any owner, and it looks suspicious, then you can send an alert to a cloud. So here the data flow is from the camera. There is some OpenCV algorithm running on a Linux, uh, on a certain Linux flavor, and you get the output, and the output is then sent out on via some cloud interface to a that can be used to store the data. And then once you have the data, you can send alerts, and you can do all sort of things. So this is like one of the brief requirements the client has given us. So then we can make into a block diagram. So we have the SECO COM-HPC. Then you have a camera interface, which could be either LAN or USB, or you have a CSI camera. What else you need? You need the power supply. You need USB connectors. So if you want to connect any mouse or keyboard when you are debugging, so you can use that. These big processors, they also sometimes may require a power supervisor. So it's like a small microcontroller that turns on certain voltage rails at a certain time. So these big processors, they have a very strict turn on and turn off sequence. So you can use it probably uses a power supervisor to do these things. And you have a fan control based on how fast you want to run the fan, based on the temperature. And since you're reading the camera feed, you need some place for the storage. So it could be a PCI for NVMe. You could also have a SATA interface, and a Wi-Fi connector for communicating either with Wi-Fi. So this is how you would probably make a block diagram. Uh, Here I want to say, if you want to save some time on making the block diagram, you could use some LLMs, and you can have it design the block diagram and have it write mermaid code. I have a blog post regarding it. Maybe I'll post a link at the end of the session on how you can quickly do that and not waste your time in this. So in future, these all blocks will become like their individual schematic diagrams. Next, we go to the PCB requirements. So now we have our list of schematics that we will have. We will also now going to define what our PCB requirements would look like. So you see how things are going. We started from the top, then we got a little deeper, and now finally we're reaching at a point where we are now defining the PCB requirements, and in next steps we'll go even deeper. And this is all before we are starting to do the layout. Some would think that once you get a product brief, you just fire your KiCad or Altium, and then you start drawing schematics and start doing the layout. You could do that, but I think this is, if you plan it properly and then do it, it becomes more streamlined, and you can go with the flow, and you have a reason for everything that you are doing. So first we start with the PCB form factor, meaning is it just a rigid PCB, or it is a rigid with some flexible components to it, or is it like a mezzanine PCB, meaning there's a daughter board, motherboard, and then what sort of interfaces it need to have, what sort of buttons that we need to have. Um, for the interfaces part, it's fairly easy. Um, let's say you have a mechanical requirement with you, uh, and that would have the cutouts for the Ethernet port, the USB port, and power connector. So in that case, you are a bit lucky because you know that these are the things you have to have. But other than that, you also need to think about all the interfaces that you would need to do the board bring up. So you would probably need to have some breakout UARTs so that you can uh, go into the bootloader and do stuff there. There are also sometimes a small a USB interface uh, so that you can upload you can flash the boot ROM and the OS onto your device, because some of these they have everything integrated, and you might just have an eMMC. So it's not like you can just plug in an SD card and start booting off of that. You probably need to flash your Linux onto the eMMC. So there are ways to do that. You need to know the interfaces that will be needed for that. Um, Next is also the power connectors. This is a big one. Um, so how you're delivering the power to the board is also very important. Um, I'm not sure if you're aware, but NVIDIA had a very big fiasco with this because of the how the power pins were connected. If there was some imbalance, some pins would overload and melt. So you need to make sure the amount of current you are sending through the connector is adequate, and you should not be in a situation where your connectors are melting. Other than that, for the buttons, it's essential to have some sort of a way to have a reset and a power switch. Sometimes these devices does not have it accessible to the user, so you might not have a reset switch or a power switch outside, but you need to have it somewhere in the boards where you can connect it temporarily. So especially when you are debugging it and when you are doing the board bring up, these things would be very helpful. um, then you also need to define the PCB stack up. Now PCB stack up is a talk on its own. Maybe we'll do it at some point, but yeah, at this point we'll just leave it at that. Also, you need to know about the manufacturer feasibility. For example, if it's a small handheld or a wearable device, how much, if there's any flex PCBs in it, how they are bending with each other, and things like that. And if it is a wearable, you also need to have some sort of weight considerations into it as well. So what sort of how heavy you can make your design, there's a limit on that. LEDs are also very interesting because you need to have the usually we have this LEDs on board for debugging, and we label it LED 1, 2, and 3, which is really not an intuitive way to label them. Usually you should have a label for each of the LEDs, like it's a power LED, it's a status LED, it's an error LED, and then you can have them actuated based on whatever goes on to it. So this will just give us an idea of what our PCB requirements are. One thing I think I missed here is the size of the PCB. So that will come from the mechanical requirements. So this will have our PCB requirements done as well. The next part is component selection. I used to take this very lightly. So I would just start adding resistors, capacitors that I normally use, and just go with it. But before you start doing that, you need to ask yourself, what is the application of this device? Because there are certain components that have some standards that are made for that application. For example, in automotive, they have this standard called AEC Q100 or something around that. Um, so those have a very high working temperature range, and they are more mechanically stable because of the vibration that goes in the automobile. But if you use a normal component and then you find out it's going to go in an automotive device, it's going to fail pretty soon. It will work for some time, but it's not going to work a long time. Then whether your device needs to comply for ROHS certification, um, you have sometimes even height restrictions in your device. So let's say if you're designing a very thin PCB, let's say for a PCB that goes in an ID card. So over there you cannot use capacitors which are very tall. So you need to have those also in mind. Um, about the assembly cost. For example, if you mix uh, through hole and SMD parts, it might get a little bit more expensive to assemble, especially if you have a step where it cannot be assembled by machine. So you have to have a manual assembly in place. So if that is the case, it's going to increase your assembly cost, and might also not uh, might also increase the reliability, decrease the reliability of the product because of a manual process in it. And again, the compliance also comes into play, which I talked about, depending on whether it's going to be military or um, uh, medical and things like that. If it's military, they require very high precision components. So if you have a 20% or 10% resistor in a design, which is in the military, it's not going to be accepted. You need to, sometimes it has like 1% or 0.5% precision in some of these designs. So this is all about the component selection that you need to understand before you start putting things in the schematic. So at this point, now you have all things ready where you can start the design of the schematic. So you start with the design of the schematic, and it's better to use separate sheets for different functionalities, and have it a hierarchical design. That will help you a lot later down the line, because I talked about this in the previous talk, that you could use these as sort of like building blocks that you could use as references for your future designs. And of course, when you're doing the design, it's better to define the rules. It depends on the EDA package that you're using, if it allows you to design, lets you define the rules in the schematic. So for example, you could define differential pairs, you could define high power traces, you can define some rooms and things like that. And it's always good to follow good practices on how you design the schematics. So it should be readable, and it should have a flow to it. You shouldn't be making it in a way so that it's hard to read. The next step also, what you need to do is to do the BOM optimization. This is also during the schematic stage. So once you have your schematic ready, you have the bill of materials. You don't so you can estimate the cost of the product. So you have your bill of materials, you know the size of the PCB, you know the number of layers in the PCB, but you have not started the layout design at this point. It's better to do the BOM optimization at this stage rather than later, because once you start the layout and then making changes, it's more time consuming, and it's going to be a more headache for you to do later on. So one story I want to share is, there was a smartwatch maker, and they found out that they can remove one small capacitor, just one 10-cent capacitor, and they were able to save $100,000 over when they sold 1 million devices. So when they manufactured 1 million devices, sorry, Just by removing one 10-cent capacitor, they were able to save $100,000, which is not trivial. It's a big amount. So you need to put the components which are absolutely needed, and you need to be smart about how you are designing your uh, uh, doing the design for a particular block. For example, um, uh, let's say if you have to do conversion from 3.3 volt to 1.8 volts, and you might use a switching power supply for that, but that might be more expensive because it needs lot more parts than you could use just a linear power supply. This is just an anecdotal example, but it depends on the use case, of course. But this is one of the places where you can potentially save money. And I prefer to do this BOM optimization whether I'm doing a production run of 10 devices versus 10,000 devices. You should always do this step because it doesn't matter on the number of units you're going to produce. It's um, just the practice of doing this, because if you have a habit of doing this, it's going to be helpful in the long run. Next, we'll talk about layout and how we do stuff. Again, I talked about this in at length in my previous talk. One of the most important things in layout is doing the placement. So again, here MCAD requirements becomes your friend, where you have these places or cutouts where you have to have the connectors. So those places are kind of locked, and then you can place other stuff around that on the PCB. Also think about the rework, how if you have to, how you're gonna rework the PCB. So don't place some very uh, thermally heavy components next to some plastic connectors, because if you're going to remove it, you have to apply a lot of hot air and it might melt the plastic which is next to it. Again, define the rules with the trace width and trace space. Have the signal integrity rules in place. Also, some traces that need impedance matching needs to be matched with their respective 50 ohm, 100 ohm, 90 ohm resistance impedance characteristics impedance. So based on that, you can define the rules. Also, doing the mounting holes before you do any of the layout is also very important. So first of all, take care of all the mechanical things before you start doing the electrical stuff, because putting mounting holes and things like that later in the design, where you have already placed some stuff, it's going to be very difficult. Even the dielectric material, this should have been defined in the PCB requirements on what sort of dielectric material you need. So it really depends on the design, how thick you want it, and what is the weave. It all quite depends on the interfaces that your PCB has. Now the next step is, people usually call it design for. So you can put almost any letter of the English alphabet in place of X, and you can make an acronym for it. You can have design for A, which is design for assembly. You can have design for seek, and design for cost, things like that. So, uh, but from my view, I think it's better to uh, do design for X, where X stands for excellence. So you do the things the proper way. And one of the things that you need to do it in a what things that you can do is you have to ask your peers for peer review. That is very helpful when you have sort of a back and forth with the design and things like that. And you can also learn a lot when you're doing this sort of peer reviews. Um, so once you have everything done, then the next step is PCB prototyping. Um, the prototypes should be as close as the final product. So it should not be the case where um, you have a PCB which is very different from the final product. It's better to have it which is as close as the final one, and also do the mechanical prototypes along with it as well, so you can test the fit of the PCB, and also uh, test the whole system within the product, so you can test it as a product. And this is a good practice to have. There was a time I remember where I sent the same prototyping files that I sent for making a test run for 10 devices, ended up for the same files ended up producing about 10,000 devices. So you need to be as close as possible to the real deal when you're doing the PCB prototypes. Next, I want to talk about compliance testing. Uh, so there are a lot of tests that go into play when you are designing a product. You have to do a lot of testing, and my motto has been always to test early and test often. So one is the functional test. Basically, that's the test that will tell you your product is working or not. Then once you have that, you also need to make a system to test the product when it is coming off of the production line. So it's not just testing one device that it works, but you need to make a whole system around it so that you can automate the testing. So when you have a production run, the testing can be done at the factory and not when you receive the product and then you test it. Next is the IP testing. This is where you test the ingress protection for uh, water and for dust and things like that. Depends on what IP rating you are aiming for. There are some standards that you can make some test jigs at um on your own and test it before you send it out to the certification labs. Again, you can for the FCC and CE testing, you should there are techniques of measuring emissions from your PCB. So you should definitely do those before you send these devices to certification labs and cross your fingers that it will pass. That's really not the way that you should do it. You should test it first and then send it, because these tests, they are not free, they are very expensive. So you need to, every time you do a test, if it fails, you have not only have to redesign the PCB, but also you have to pay again for the test. So it adds the cost up very, very quickly. Then there's also software compliance as well. um, uh, I'm not sure for others, but for sure for automotive industry, there are these compliance tests that your code has to meet a certain standard for testing. So um, yeah, next is the resources where you can find more things. One of the things is the app notes, which are uh, written by engineers, and the the people who design the product, who are selling the product, they have made these app notes, and these are really, really helpful when you are making anything. So if you have a chip or some IC, you should look at the app note for it and see how it is designed. Uh, Listening to podcasts is also a good way to learn about these stories and learn about these anecdotes, and be aware of the things that can go wrong by the people who have already been in this kind of situation before, so you don't end up in those. And the best way is, according to me, is just learning by doing it. You need to make mistakes, and there's no other way to go about it. Reading, listening to podcasts and things like that, yes, it helps, but the thing that will help you the most is learning by doing. So make more devices, make more products. Try to find holes that you missed. Try to find some places where it is not that you could have improved, and things like that. So this brings almost to the end of my talk, and let's uh, for the next talk, I think we'll probably talk about more detail on the power supply system for the device. And if there's any questions, let's have a look. Let's have it.
Yeah, there are a couple of questions. The first one here is which tests are included in CE? That's not a short list, I don't think.
Uh, Mostly they are CE is like a bit broad, but there are these emission tests that are also done for electronics. So there are certain they basically, in layman's term, it is your product should not transmit unwanted signals, and the second is, if unwanted signals are transmitted to your product, it should still function. That's the basic gist of the CE test, and even the FCC as well.
Great. We've got a couple other chats coming in, Ravi. Yeah, just please continue asking your questions. So for me, I guess, besides the requirements that are coming in from, the client, does your mindset, do things change about how you approach a design if, say, you're looking at a Linux class system that's got a multi-core NPU versus, a microcontroller based system, that's doing something very simple. Obviously, the number of layers you're going to use is probably going to change, but is the thought process all the same?
Yeah, it's the same. It doesn't matter if it's like a microcontroller or a microprocessor. It's always good to have this sort of a framework through which you go through, and this will make sure that you don't miss anything in between. So, for example, let's say even if it is a simple system and you just jump in and start designing stuff, you might find later on that. Uh, this happened as well with me. But it was like I got a requirement to design a PCB, and then after designing the PCB, I found it's supposed to be used in automotive industry. So yeah, not it was not a happy conversation, but yeah.
Yes, changes everything. Is ROHS included in the case of CE tests? Always?
I think RoHS has its own separate certification.
Yeah.
So they would probably just check your bomb and thing. But yeah, but CE might also include RoHS as well. So it's it could be two. I'm not entirely sure
Hmm.
of what the scope of the CE is. It depends on what you. There are like certain standards within the CE as well, I think, that you need to target for. So yeah.
All right. Here's a question from Taj. I want to make a STM32 board with an ESP module and some sensors. After a bit of work, it feels a little bit overwhelming. Did you feel the same as a beginner, and how did you make your way past the first hill?
Sure. Yeah, yeah. This is a very natural thing to feel. Uh, there's nothing wrong in it. It's just the way you approach this is like take a small chunk and just work on that, and just keep on doing that consistently. I think this advice is given all around, but it actually works. Just it does feel overwhelming, but start at some point and keep working through it little by little, and before you know it, you will have your PCB with you.
So I'm sure we're going to get into this a little bit more as we move forward. But of course, the platform that Ming was using, that COM-HPC, it's an Intel Raptor Lake. What Taj just mentioned, the STM32. It's a far cry from that, right? It's many more cores, consumes a lot more power. When you start thinking about there was a question before about power integrity versus signal integrity, and I don't want to answer a question that general, but I do want to ask, when you have a consideration between something that large versus what Taj is talking about, how does it change your design?
So when you're a beginner, you don't really care or even know about signal integrity problems. But as you go a bit more into stuff like high-speed design, like USB, Ethernet, and things like that, then you need to start learning about signal integrity. And when you learn those things, and then you also start applying the same principles to the simpler designs, that makes that design even more robust and reliable. So, for example, using your ground plane as a reference, and not cutting up your ground plane and things like that. Again, these are like topics and talks on their own, but if you know about signal integrity and at a later stage, and then you even apply it on your previous design, you would for sure have a very you can design things with confidence that your device will pass this CE certifications, the emissions test, etc.
That's great. Yeah, and I do think, like Hemal was mentioning, as we move forward, and especially as we start using that particular design as a reference, or others, it does give us the ability for people like Taj, or for who else was asking a question, Krishnamkur, like the thing that we're going to encounter in some cases are topics that are not that are more advanced and deal directly with problems like signal integrity, because the processors are bigger, they're running at faster clock or higher clock frequencies. We're using interfaces like PCI Express and USB, and things like that. So there will definitely be some hands-on or more in-depth look at some of those topics. Naman's been typing here for a while, so this is either he's having computer issues, or this is going to be a mammoth question. Any software suggestion we can practice schematic design? So any tools that you recommend?
Just for schematic design, I don't think the software usually come as a suite of software. So KiCad is just the number one open source project right now, where you can do schematic design, even also do the PCB design as well. So yeah, KiCad.
Great. All right. Well, there's a unabashed advertisement for KiCad. Would I say KiCad? So that'll bring us to the end today. Thanks everybody for attending. I really appreciate your time and attention. And Hemal, good stuff as always. Really enjoy it, and looking forward to doing more of these. What did you say the next session was on, by the way?
Power supply design for the SECO board for the COM-HPC.
That's great. So if you're new to that realm in the industry, tune in, keep your eyes peeled. We'll be sending out information on when and where that'll take place. It'll take place where you are right now, but exactly when, we'll let you know very soon. And then also Embedded World 2025 is next week. we will be there. Well, me and some of the other dev heads, Ming, Zach will be there. Hemal will not, but keep your eyes peeled on the server and in the on the website. I've just dropped both of those into the chat channel there, and you can check out what we're seeing at the show, what we're doing at the show. We've got a bunch of cool announcements around some new tools that we've developed for engineers that will allow you to evaluate and prototype things more quickly, and we're really excited. So we'll be at Embedded World. They helped us out with the booth, so I want to give them some thumbs up for that. And if you're going to be there, feel free to drop me a line, either on LinkedIn or in the Discord server or elsewhere in the community, and we'll see if we can sync up. But thanks a lot, Hemal. Good stuff as always, and we'll see all of you guys in the community, discord.gg/devheads, devheads.io. We'll see you later.